class, I was up to here. So far I remember. Huh? Line rotation. Notation. Okay, up to this, huh? Fine. So let's start now. Next topic, batteries. Please switch off the fan. Batteries or galvanic cells. Now batteries, for example, just look at the picture here. There are cathodes and anodes. And fortunately I was into some battery company for some time. So I have seen actually how the batteries are made. This, I'm talking about this storage battery, this type of battery. There are two types of plates. One is lead plate. Silence. One is lead plate. And these lead plates are made by casting. Obviously, casting means dhalai. Yes, casting. That is called casting. You have heard the name cast iron. So it is also casted. That's why cast iron. So here these lead plates are casted. And it's like a grid, not a flat sheet. These lead plates are like looking like a grid. Grid person, this is like a wire mesh or net type of thing. That is made of grid. Lead plates are made like a grid. And another plate is there, that is called lead oxide plate. Oxide is a powder. So that you cannot make a plate out of that. It's because it's a powder. So make a paste out of this powder, lead oxide powder, and that is applied into this lead plate grid to make lead oxide plates. So two types of plates are there. One is lead plate and one is lead oxide plate. Lead plates are just the grid system, and lead oxide plate is made of the same grid but it is coated with some lead oxide paste. Okay. Now here we see the reaction. Pb plus PbO2 plus H2SO4 equal to PbSO4 plus H2. That is the reaction. Now there will be two reactions just opposing each other. One is charging, other is discharging, because this is rechargeable system. This is rechargeable, that's why charging and discharging.
Why we are using the lead?
Because this particular both way direction reaction is found to be best suitable for this, because this is a matter of practical experience. We can use so many other things, but practically found for rechargeable system, it is the best one. Why? Why? Because most of the time what happens, the metals is getting degraded very fast, means falling down at the bottom of the solution. As a powder or is a small flakes, yes, falling down at the bottom. But lead is the only metal is found that you can go for discharging and charging over so many number of cycles. Normally 600 cycles is very common for a small battery, but for larger battery it can be longer, because larger battery can withstand more. Why? Because you have a bigger plate, na? So if some portion is damaged also, physically damaged, other portion can be utilizable. So that way it will run much longer. That way the plates are made. So there is a casting system. Molten lead is poured into that. Hey, everyone must listen, don't talk. This lead is in the molten condition, is put into some casting system. After that, these two, both, it is coming from both sides. The casting system is coming from both sides, and there is a grooves and holes, and you are filling that grooves and holes with molten lead. And by the way, another reason, lead can be, you can make it molten instead quite easily. No melting comparatively, not very high melting. Very high melting is actually disadvantageous, because whenever high melting, you have to use lot of fuel, so to raise the high temperature. That is not economical, number one. And if you go at a higher temperature, there will be more and more corrosion, damage. The whole system damages faster. So that's why you have to always look for a material which will be, that is the material science. You have to always look for a material that will be durable, convenient, low temperature casting possible. So that type of material you need. That's why. That is the reason we are choosing lead. And lead is a very popular one and long time people are using. Though lead is toxic material. But this lead we are not getting exposed every day. Though it is a toxic material, we are not getting exposed to it. It is totally contained and sealed system. Achha, by the way, so two types of plates are there. One is black color plate, that is PbO2 plate. Another one is grey color plate, that is PB plate. Lead plates are grey color and PbO2 is black color. So these two plates easily recognizable. One is grey and another is black. So this in between there are some plastic separator. So multiple number of anode and cathode are kept together one after another. So PbO2 is getting reduced and Pb is getting oxidized naturally. So Pb is getting oxidized and PbO2 is getting reduced. And on it will be opposite also if you go for charging. So charging and discharging opposite two reactions. What will be the reaction? Pb plus H2SO4 suppose. PbSO4 plus H plus. Half reaction. You understand half reaction? Actually, if you analyze a complete cell, there are two compartments, cathodic and anodic compartment. So in anodic compartment oxidation and cathodic compartment reduction. So here also it must be the same cathodic and anodic, but there is no separate compartment in this case because we are making a series of plates. So there are no two components separately. So you have a one cathode, another anode. In between there is a separator, cathode, separator, anode, separator, cathode, separator, anode. That way it is placed. So all these positive plates connected together, and all the negative plates are connected together, and we are getting two terminals. Okay, two terminals are fitted on the top of the battery here. Positive terminal and negative terminal. All the positive plates are connected together to make you positive terminal. All the negative plates are connected together to make you the negative terminal. So that is at the two ends of the battery. A big battery. Here we have one terminal. Here we have another terminal. Quite separated to avoid the short circuit. Sometimes you can, when we are pouring water into the system, we have to add water. You know, at least 5 liter water required every 6 months. Okay. 5 to 6 liter water will be required every 6 months. Why? Why that much of water required? Distilled water. You have to buy distilled water and pour it there. Okay, not ordinary water. Because ordinary water contains ions. No, other undesirable ions will be there, which will reduce the efficiency of the battery. That's why you have to always add distilled water. Why? To maintain the concentration, whatever was there at the beginning. And why water is added? Because actually we are using some 50% H2SO4 solution, and that is getting electrolyzed, and due to electrolysis hydrogen gas, oxygen gas generated. Water analysis, hydrolysis. So hydrogen and oxygen. So these two will be bubbling through, going out in the atmosphere, slowly getting dissipated in the air. Hydrogen and oxygen. We cannot collect that because it is not so large quantity that it will be economically beneficial. So we are allowing it to leave it to the atmosphere. So every 6 months, 5 to 6 liter water is getting electrolyzed. That's why you have to refill to make the same concentration back. Otherwise, it will be like a very concentrated solution and it will damage the whole system. Got it? So that is the idea. Cathode anode in between plastic separators. And these are also perforated separator, so that solution can pass through, but the plates should not come in contact. Plates will not come in contact, but they will be perforated plastic material. And plastics are, as a separator, very good. Plastic as a separator is very good. Usually these plastics are polythene plastics. And why it is good? Because it is not react with any acid. Plastic is that way it is good because our acids are also coming into plastic containers, polythene containers. That means plastic is acid proof. This plastic container, that UDP, LDP, high density polyethylene, low density polyethylene, these types of jerrycans, these are, you have seen soft jerrycan, if you press it will be compressed and then coming back, some sort of elasticity plus. These are called LDP. And you have seen our big container, distilled water is kept into that, into the laboratory. These are also plastic, but these are high density polyethylene, HDP, high density polyethylene. Okay, so these high density polyethylene, low density polyethylene, these are usually white colored. So these plastics are used here also in between. Sometimes it is a bit black color, not exactly white. So in between these plastics are there, and 50% H2SO4, and time to time we have to add water, and maybe after a few years you have to replace the acid also. After a few years you can replace the acid. Okay, you will get some performance again for some time. If you replace this acid, it will run for a longer period. Okay. So that is about the battery.
Sir, what is this cell divider in between those plates?
These compartments are sometimes this cell divider may be used, or otherwise the plastic separators can be used. Cell divider if you use, then cathodic compartment and anodic compartment you can make totally separated. So in that case it will be initial cost will be a bit higher. If you make this type of battery, then initial costing will be a bit higher. Otherwise, if you use separator, the initial cost will be cheaper. But maintenance plastic can be damaged after 5-6 years. You have to maintain and you just check what is the condition of the plastic. And what is physical damage? If you go for charging and discharging, slowly some of the powdery material like PbO2 falling down at the bottom, that you cannot avoid. Physical damage. Slowly it is getting deposited at the bottom. So up to 5-6 years there will be no problem. And then the quality goes down, means performance goes down. Initially when you buy the inverter, the battery, it will run for maybe 10 hours, 12 hours. But with time it degrades and it will run for 6 hours, 5 hours, 4 hours. Whenever there is a power failure, I am talking about that. Okay. So charging, discharging going on, but the performance is going down. Why it is? Because the physical damage is happening. Earlier you thought that this is my total surface area of the plate. Now surface area of the plates are getting damaged in different places. So obviously overall surface area will not getting, na? So the capacity is going down. Voltage is constant, but capacity is going down. So already I told you yesterday one thing, capacity and voltage. Voltage depends on how many plates, and capacity depends on size of the plates. If you make the size of the plate larger, your capacity of the battery will increase. And if you increase the number of plates, voltage of the battery will increase. Now dry cell. One thing. Yes. So Pb plus H2SO4, half cell reaction I was talking about. Pb plus H2SO4, you get PbSO4 plus 2H plus. That sort of reaction. Now PbO2 plus H2SO4, again you are getting PbSO4. Okay, PbO2 plus H2SO4 is also giving you PbSO4. Because you right hand side you are having only PbSO4, just see. It is giving arrow means it is not balanced. You can make it balanced. So PbO2 plus H2SO4 is also giving you PbSO4 plus H2. H2. So plus you will have to take this H2SO4 means H plus plus SO4 2 minus. So that way if you consider, so if PbO2 is giving you H2O, taking oxygen from here and hydrogen from here, you are getting water, and ultimate product is PbSO4. But if you give the discharging reaction, then opposite reaction will take place. Now dry shell. Dry shell is this we are using in the torch battery that we are using to torch our remote, your wall clock. We are using the battery, that type of battery. So zinc is there as the container. Yesterday I was telling you that zinc container is there. So yes, so this is the zinc. Zinc is used in the container itself. Sometimes we are not exposing zinc out in the atmosphere. Otherwise, the zinc surface can be degraded. That's why it is covered with another metallic content. That's why you cannot see the zinc, and you think it is a tin. Some of you told, I think you told that it is made of tin, looking like that. Because it is another coating given over this, just to protect the zinc also. Why? Because zinc is highly oxidizing material. It is getting oxidized so easily. It is prone to be oxidized. Itself is reducing material, but the zinc is reducing material, but itself getting oxidized so easily. So that is aerial oxidation. To avoid the aerial oxidation, we are giving another coating covering.
If we remove the tin coats, then we will get a plastic cover.
Hmm. No, some zinc must be there. Otherwise, this tin is not tin. Tin is iron. When we normally call tin set, it is actually iron. So here iron is not that effective. And hmm? Some zinc must be there. Should be there somewhere. Acha, because inside it may be there, but maybe it is fused. These two things are fused together, making some alloy. Something possible. And in between there is a rod, graphite rod. And see, this ammonium plus iron zone actually is ammonium chloride. And some MnO2 is there just to catalyze the reaction. So to make it the reaction faster, otherwise this MnO2 is also reacting here. So this is forming NH3. So this NH3 is a gas. So there should be some gas vein, and the gas is slowly going out. And after some period, this battery is losing its property, and then the leak out is there. You can find that there is some leakage. The solution is coming out, and then the battery life is gone. Yes, the paste is there, paste, and this is made of ammonium chloride and this MnO2 mixture.
But sir, in each reaction we get the water.
Hmm.
Like the water one.
Evaporated to some slowly getting, because it is not huge quantity water, very little bit of water, so that is leaked out afterwards. I told them there is a leakage, that water is produced, and that's why the leakage is there, because the liquid comes out along with the gas, then the liquid comes out. And initially at the beginning, when the reaction is in the right form, then little bit of water is produced and that is getting evaporated. Because the rate of production of water here is very slow, not very high. Acha. Electrolysis, running a galvanic cell backward means opposite sort of reaction. Using electricity, producing some new material. That is our electrolysis. Acha, what is the application of electrolysis? Electrotyping, electroplating, the nameplate, making the nameplate, they are using the electrolysis. Okay. So, any other application? Refining of metal, like copper. Copper is impure copper, you can use as a anode, and pure copper you can take as cathode. Then impure copper will be dissolved more and more, and pure copper will become thicker. That way we refine copper. That is called electro-refining of copper. That is a good application. Electrolysis has a lot of application. Manufacturing of sodium, magnesium, this type of metal manufacturing is done by electrolysis. Directly by any reaction you cannot get it. This electrolysis is actually reduction. By electrolysis you are reducing the material. Like alumina. From alumina you are preparing aluminium by a process, electrolysis process. Okay. So these are the applications of electrolysis. Now, whenever doing the electrolysis, there is some formula we are using. Q equal to I into T, ampere into time. The amount of current in coulomb is equal to ampere into time. Ampere into time is coulomb here. Okay. So, how much time the current should be applied? So, these things can be calculated for any type of coating. So, there is a numerical. I think you have done that numerical earlier. Current into time equal to charge, total charge. Charge by Faraday. Faraday is F normally, 96500, that Faraday. So 1 Faraday means 1 mole of electron. These are some basic ideas, minimum ideas. Anode is giving oxidation reaction is happening at the anode, and reduction reaction is happening at the cathode.
So 1 mole of electron?
1 mole of electron means Avogadro number of electron. 6.023 10 to the power 10. Yes. So electrolytic cell voltage applied to make anode positive. Anyway, so these are some voltaic cell reaction, Daniel cell, as I was talking yesterday. So here zinc is giving Zn2 plus 2e, and reduction occurring at the cathode, Cu2 plus 2e equal to copper. This is called Daniel cell. Nernst equation, EMF equal to EMF of the anode minus EMF of the cathode. Minus, why minus? Because here we are taking both in the same sort of half cell EMF. same pattern means both are oxidizing potential or reduction potential. If you use both oxidation potential or both reduction potential, then one must be negative. But if you take actually anode, oxidation happening at anode and reduction is happening at the cathode, that way if you take E equal to E anode plus E cathode, that is quite right. So here Zn2 plus plus, this is the Nernst equation. So what is the basis of the Nernst equation? That is called Van 't Hoff isotherm. The basis of the Nernst equation is Van 't Hoff isotherm. Del G equal to del G naught plus RT ln K. Have you heard the equation? Del G equal to del G naught. Del G you know, free energy change. Already I have discussed thermodynamics. So del G equal to minus NFE. What is that del G? Del G is free energy change. Del G naught, free energy change at the standard state. And there is a relationship del G equal to del G naught plus RT ln K. This equation. Okay. Now del G equal to minus NFE and del G naught is minus NFE naught. Then if you divide both sides by minus NF, you get E equal to E naught minus RT. Now minus will come. Okay. Because you are dividing by minus NF. So that's why E equal to E naught minus RT by NF log K. And that log is ln actually. Log E base log. So now 2.303 if you multiply, it will become log 10 as our normal relationship. So finally we get a relation E equal to E naught minus 0.059 by n log 10 K.
So K is what?
K is the equilibrium constant for the reaction. Any reaction you are considering, the equilibrium constant for the reaction. That means the product concentration divided by reactant concentration. Okay, whenever the equilibrium is achieved, then product concentration by reactant concentration is the equilibrium constant. K. So it is in front of you. This is the reaction. So this R is actually 4. 4 is N actually. So this is the equation you can take. So these are actually same. I see.
NF होगा ना?
No, actually this and this equation are same because NF के जगह 2F because here we are taking 2. At here electron is 2 electron, na? So that's why N is 2. And if I take this equation, then it is becoming 4. But practically same because here square is there. This and this equation is not coming different. It is coming same only. So if you take this equation, then you get this, and if you take this equation, you get this. That is, if you make it double or 4 times, that does not matter. Ultimately, you are getting the same. So this Nernst equation, these values if you put R equal to 8.314, T equal to 298, F equal to 96500 or 496, 96496 to be very precise. Okay, if you put that 496, no 500 is taken for our simplicity of calculation. Otherwise actually 496, 96496. 96000 is taken for simplicity of calculation. Less calculation, zeros are you are getting, that's why. So now these values if you put here, then you get 0.05916 by n V and log AC by EV. Based on this equation, we are getting this Nernst equation. Now this EMF is calculated like this, E plus minus E minus. So just follow this. If you have any doubt, then tell me. Acha, by the way, where is your E naught? For first reaction, there is no E naught because it is EH plus H2 equal to 0. E naught is 0 for the first equation, reaction, this reaction. This reaction E equal to E naught minus RT ln K, no? So this E naught is 0 in this case because standard state hydrogen atom. So whenever you are taking hydrogen man at the standard state it will be 0. So E naught value will be 0. So that's why see here 0 is E naught is missing. No E naught there because it is 0. So
What about the bottom one, sir? What about the bottom?
bottom one it is not standard, so that's why the value is applied.
What is the standard?
Standard value is 0.76 volt. Zinc-zinc-ion is 0.76 volt. That is applied. Zinc-zinc-ion. So 0.76 volt. Copper-ion 0.34 volt. These two I remember because it is this galvanic cell. Galvanic cell is the best example. That's why remember the values also. Okay, Zn 2 plus value is 0.76 volt and copper 2 plus copper value is 0.34 volt. So here this 0.76 volt is applied because it is zinc ion, and finally we are getting this relationship. This is an example, just for a clarification. What is how the EMF is calculated and all. This is your explanation. This is the way EMF is calculated. You have a cell reaction, half cell reaction, two half cell reactions, you are getting total cell reaction, and well, after that you put the values and you get that relationship.
So हाइड्रोजन E0 वाला H plus से H2 हो रहा है तो उधर भी तो एक
No. We are considering is 0 because it is a reference frame. Above hydrogen you have certain ions and below hydrogen you have some other ions. So it is taken as the reference frame in the middle. That's why hydrogen is considered 0. Yes. We are making considering is 0. Based on that we are making the relative chart. Relative chart. So this is redox reaction, oxidation reaction, voltaic cell, copper electrode dipped into a solution of copper to sulfate. Just examples. Zinc electrode dipped into a solution of zinc sulfate. I think last day I could not complete one thing. Let me clarify that once again. I was discussing that Helmholtz double layer. But at the end I was discussing. That's why I could not find time. Just let me clarify now once again. You have some solution and zinc, let it be zinc sulfate solution. In that you have just dipped into some zinc rod into that. Then what will happen? Zinc has a natural tendency to get oxidized. That's why it will form Zn2 plus ion. A few molecule, not large. A few molecule dissolve like this. See, it is getting dissolved. Okay, slowly getting dissolved. That's why the surface is uneven, getting dissolved. So zinc is getting dissolved, going into the solution, forming Zn2 plus, where the electron will be there. The electrons will be residing back. It will stay back at the metal itself because it has got no stability in the solution. So electron will stay back at the metal plate itself. Now, as the electrons are there on the surface of the metal, it is becoming negative. Once it is become negative, no further dissolution can take place. It is giving resistance. Because it is becoming more and more difficult. Why? Inter-electron repulsion factor. Electron is already there, so it cannot release any more electron there over there. So it is already negatively charged. That is resisting itself. Okay, so that's why the reaction will be stopped immediately. After a few molecule dissolution, it will be stopped. Then what will happen? It is already become negative. Now water molecules in the vicinity, they are considered as dipole. Plus and minus side is there. So it will orient itself. The molecule will orient itself. Suppose this is plus side and this is minus side. Now this is minus. So it will orient itself like this. This is already minus charged. Now this molecule, water molecule, this is a water molecule if I imagine. Now this side is your plus side and this is your minus side if you consider like that way. So it is a dipole, na? So it will orient itself like this. Plus side will orient towards the minus plate. And so within a few micrometer gap there will be two layers, one on the surface, another in the solution. That's why it is called double layer. One layer, negative layer there on the surface of the metal, another layer, positive charge, a few millimeter gap, but it cannot
create a potential difference.
Yes, that is creating a potential, not difference, creating some potential. And due to oxidation this potential is generated, that's why we will call it oxidation potential. On the other hand, if you have a copper rod, just immerse in the copper solution, copper sulfate or copper chloride, it just dissolve, dipped into that. Then what will happen? Copper has got a natural tendency to get reduced. So copper will become Cu2 plus 2E. So it will deposit itself, not dissolve. It will deposit itself from the copper ion will deposit itself on the copper surface. So it is already positive because Cu2 plus is getting deposited. Where from it will get the electron? Not available. So electron it will have to take from the metal plate itself because free electrons available on the metal only. So it will accept some of the electrons from here and it will itself become copper. So this copper rod will become positively charged now. Naturally, positively charged. Now, these water molecules are the same. So they will orient itself just in opposite direction. Earlier it was orienting this way, now it will be orienting this way.
The negative will attract.
Yes, because of that attraction. So here there is a positive charge surface and there is a negative charge this portion of the water molecules surrounding it. So then there is a plus 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 and minus minus minus. Again there is a double layer. And this is due to the reduction reaction taking place, so it is reduction potential. Now in one case it is oxidation potential and the other case it is reduction potential, cathodic compartment and anodic compartment. Okay, now after that, no further reaction is happening because there is no contact, there is no circuit completed. After that, if you join this copper and zinc by some wire, what will happen? One is plus and another is minus. Zinc is minus and copper is plus. You are joining by wire. What will happen? Current will flow, but it is only momentarily. Little bit of flow. Because it is very much restricted. Only few molecules was charged. So it will immediately discharge. And the reaction will not continue. Okay. Reaction will continue if you make a connection between the solution and solution. And that is done by solvents. This black color, this inverted tube filled by agar-agar gel and KCl or KNO3. This is inverted here. This solution to solution contact making the circuit complete. And then only current will flow, will occur, and reaction will continue, and you get a continuous supply of current for some period.
So here agar-agar gel का कोई importance है?
agar-agar gel का importance उसको पकड़ के रखेगा कौन? Solution is actually liquid ना. This KCl or KNO3, if you just make a solution and put into that U tube and if you invert, all solution will fall down. So that's why gel-like substance will be required, and agar-agar gel is just a gel for that purpose, just to hold the solution in the tube itself. Otherwise, it will fall. Achha, yesterday I was in a FDP. Suddenly I got some new idea. That's why I want to share with you. We are always talking solar energy is very good. Okay, go to solar. Talking about that. See the practical problem. Suddenly, if there is a cloud in the sky. Yesterday that was the discussion. That's why I'm sharing with you. So if suddenly there is a cloud on the sky, so suppose the 500 megawatt electricity was generated by the this grid, by this power grid. Suddenly it will come down to 100 megawatt, and there will be huge blackout into the whole city that we cannot avoid. Got it? So that is a very serious problem. How can we overcome that? There can be cloud anytime, na? Suddenly, up and down will be there. Production will be suddenly stopped or dropped. Production will be dropped. That is how can you avoid?
Backup रखेंगे हम लोग.
कैसे?
Backup रखेंगे.
बैटरी?
हाँ.
बैटरी का पावर कितना है? बैटरी कितना? हाउ मच बैटरी? बैटरी नहीं होता भाई. प्रैक्टिकल नहीं है. प्रैक्टिकल नहीं है. देखो, एक मिनट. 13.5 lakh we have invested here at BCRI at the top of our building. It is already solar panels are there. हमारे इधर है ना? We have not bought any battery. Why not? Because it will be totally uneconomical. बैटरी खरीद के उसको स्टोर नहीं कर पाएंगे, इसलिए हम लोग क्या कर रहे हैं? What we are doing? We are producing the current and giving in the grid. And what is our benefit? We have a two-way meter. Whenever we are producing and giving in the grid, we are getting that our consumption is less. And when you are, that means there is a sort of compensation mechanism. Some amount we are producing and releasing in the grid. It is called two-way meter. So when we are taking from the grid, our meter is running. When we are giving to the grid, it is going in the opposite direction. Meter is running in the opposite direction. And net bill we are paying. That is our only advantage, nothing else. And battery, it is not at all economical, not possible, not feasible. Otherwise, we could run our college by our grid power, na? It's not possible. Costly, very costly. Battery is very costly, and that is not at all economical. Hydrogen electrode, yes, actually you are talking about hydrogen electrode, how, and all this thing, na? Just see, this is the actual system. You have a solution In between, in this you have some hydrogen bubbling system. You can bubble through. So, and here there is a platinum electrode. What is platinum? On the platinum surface, fresh deposition of platinum. You have a platinum surface, on that fresh deposition of electroplating of platinum, so that surface becomes a bit rough. So that if it is rough, then whenever hydrogen bubbles are formed, it can leave the surface. And if it is very smooth, it will stick to the surface. That's why we make it rough purposefully. So it is called platinum. What is platinum? Platinum deposition, fresh platinum deposition on the surface of platinum. Time to time we have to do that. You have to clean the grease material, oily material if sticking to the surface. Otherwise, the bubble that is formed, it will stick to the surface and it will hinder the further reaction. So we allow the reaction to take place. Sometimes we may need to brush it up to remove the hydrogen gas, etc. Otherwise, some potential opposite direction, some potential generated, that is called junction potential, and after that we have to apply more voltage to overcome the problem, that is called over voltage. So electrochemical cell using Zn2 plus Zn, half cell and a standard hydrogen electrode. What is the purpose? You have to get the values. In the electrochemical cell is, we write the EMF values. Zn2 plus 0.76. How do you get it? This is the way we get it. Because you see that all these values, if you want to make a chart, so you have to get the half cell potential. But half cell, how do you measure? Until unless you have a complex circuit, current will not flow. Current must flow. So that's why one half cell will be zinc ion, or another half cell will be hydrogen. One half cell can be copper ion, other half cell will be hydrogen ion. So this hydrogen ion is taken as always at the half cell, because that way you can get the half cell potential of all the other systems. Copper ion, zinc ion, everyone you can find out. One by one. And then you make a chart, that is called electrochemical series. Got it? Electrochemical series, how do you make it? This is the cloud, this is the pairing. After this pairing, this hydrogen is taken as 0, and this part is have some value, suppose x. Now you get the measurement of the total potential. From that you can find, you deduct 0. That means itself whatever you are getting, that is the half cell potential of the this half cell, this particular half cell, zinc ion, copper ion, any one you can find out. This is copper ion, half cell potential. By the way, one more thing. When you are taking zinc ion and hydrogen ion, then zinc is taken as the anode. Here, just see, there is in the left. Kept in the left is anode. It is kept in the left, so it is anode. Whereas when you take copper ion, it is opposite. You see, it will be negative compared to this. Here copper, zinc ion, this Zn plus H2 plus it will be Zn H2, but copper cannot do that. So it is in the opposite side. Hydrogen is the left side. You see, here hydrogen was in the right side, hydrogen is produced, but here hydrogen is not. Yes, here hydrogen is in the left side. In case of copper, it is in the right side. It means it is not hydrogen producing hydrogen. It is utilizing hydrogen, not producing hydrogen. And the hydrogen is actually supplied. Atmospheric pressure hydrogen. So what are the conditions? 1 molar HCl, atmospheric pressure hydrogen, and platinum electrode, which is considered inert electrode. These are the 3 conditions applied for SHE, standard hydrogen electrode. We call it SHE, standard hydrogen electrode. Okay. So the standard reduction potential. Standard potential means this. Means standard means what? 25 degrees centigrade, atmospheric pressure maintained, and the solution should be molar. Concentration of solution should be molar. Then it will be standard. Now, always standard hydrogen electrode is not the only standard electrode. There can be other standard half cell also, like calomel electrode. Calomel, C-A-L-O-M-E-L, calomel electrode. Mercurous chloride, KCl, that combination. Mercury, you have a tube. It's not here, so right now let me tell this. You have a tube. At the bottom of the tube you have some mercury. Through the and from the bottom you have passed through one platinum wire. Okay. This platinum wire has got no purpose. You have to connect it with some wire, na? That's why the platinum is inserted. You cannot connect it with mercury. Mercury is liquid. So how can you connect wire into liquid? Not possible, na? That's why this platinum is inserted into the mercury. So, but actually the mercury is the electrode in this case. And after, no, not electrode, mercury is the contacting material. And on that you have the KCl. KCl means Cl minus, and you have Hg2Cl2 and Hg, Hg2Cl2 and KCl. These are the things. And on that top you have a cap. There is a side guard, side tube also. Through that you can replace KCl sometimes. You can refill the KCl solution. So that is also a standard one. But standard does not mean always zero. For hydrogen ion, we are taking standard and there it is zero. But it is not very portable system. Hydrogen ion 1, gas, na? Handling difficult. Can you carry hydrogen cylinder here and there? Difficult, no? Handling difficult. That's why calcium electrode is popular. It is very small one, like this. You can carry, you can take it anywhere, connect it anywhere. That is the facility. Portability. And it's not portable. Hydrogen ion 1 is not portable one. You have a cylinder, bubbling system. You have to carry this container. It's clumsy, isn't it? Just see, this is clumsy. So that's why this another one is also used. It is called calcium electrode. Okay, these standards are made. I think I have already more or less completed. Now standard cell potential. Just like your standard half cell, you talk about standard cell. Okay, there can be standard cell also. Western cadmium cell, that is a standard cell. Why standard cell required? First of all, why half cell required, half cell standard required? Just to find out the half cell potential of other systems. Okay, cathodic system, anodic system, to find out the half cell potential. If you know the half cell, then you can connect the half cells to make a complete cell and you can get the EMF. This is the way. Now, what is the purpose of a standard cell? Standard cell is to know your EMF will be known EMF. That's why. Standard cell, your EMF will be known EMF. That's why the standard cells are required. Calcium electrode, I told you, the EMF is not 0. 0.2242 volt for standard for KCl, for saturated KCl. If you take saturated KCl, let me draw it as I discussed already. It is something like this. I am taking care of that. This is mercury, this is platinum, this is mercury inside. Now we have some KCl solution on the top, and here we have the cord. That's all. And voltage is 0.2422 volt at 25 degree Celsius. So known values, and its temperature is EMF is temperature dependent. That's why temperature I have mentioned. Okay, I can end it here. That's all. So today this electrochemistry part is also completed.